Now it's time to shift gears from absorbing ideas to actively using them. You've been exposed to decomposition methods, thinking frameworks, and analytical approaches. This is where they come alive. The task ahead is simple in intent, but powerful in impact. Take a situation or scenario, break it down into its meaningful parts, and then understand how those parts relate to one another. We'll start by learning how to decompose a scenario into layers: inputs, actions, covariance, invariance, time-dependent, and time-independent, and then place those elements into a clear framework that helps you see structure instead of complexity. Once the pieces are visible, the next step is to connect them. Which parts influence others, which ones depend on something else, and where the real leverage points lie. To make this concrete, we'll walk through a familiar archery scenario and build a decomposed, correlated view of its inputs and functions. This is not about archery itself, it's about learning the method. That example will act as a reference point, so you can then apply the same mechanism to a scenario of your own choosing. If you can reach a point where you can confidently decompose a situation, map its layers, and explain the relationships between its parts, then you've achieved exactly what this stage is meant to deliver: clarity through structure and understanding through connection. Let's slow this down and build a clear mental picture of the framework before we start using it. At its core, this framework is an 8-part construct. When you apply it to any subject or scenario, you are deliberately examining 8 distinct aspects of that situation. We'll get into what those 8 aspects are shortly, but first, it's important to understand how these 8 parts are organized and why they matter. Out of the 8 parts, 4 belong to what we call the outcome domain. This is the crisscross marked areas of the framework, the space where you plot what the scenario produces, how it behaves, and how effective it becomes. The remaining 4 parts belong to the input side. We don't explicitly mark these as a separate domain because inputs are assumed to be the starting point. They quietly feed the system. What matters is how these inputs transform into outcomes. Now there's another important dimension layered on top of this structure: time. Out of the 8 parts, 4 are designated as time domain areas, 2 on the input side and 2 on the outcome side. These are used when inputs or outputs change over time. So in this framework, you are not only distinguishing between inputs and outcomes, but also between what is static and what evolves. Let's now walk through what each part represents. On the input side, one area is used to capture inputs that form the foundational basis of the scenario. Inputs where more of them typically improves the overall effectiveness. This area is called positive covariance of inputs. Think of these as inputs that directly strengthen the system when they increase. Just below that sits the negative covariance of inputs area. This is where you plot inputs that behave in the opposite way, inputs where less of them actually improves the scenario. These inputs have an inverse relationship with effectiveness. Directly adjacent to these are the outcome side counterparts. The positive covariance of functions area captures outputs or functions where increased production signals better performance or improved results. In contrast, the negative covariance of functions area is where you place outcomes that, when reduced, improve overall effectiveness. These four areas together give you a static snapshot of how inputs convert into outcomes. Now we replicate this exact logic for time-varying elements. You get positive and negative covariance of time-dependent inputs and positive and negative covariance of time-dependent functions. These areas are used when inputs or outputs fluctuate over time, and their increase or decrease changes the scenario's effectiveness dynamically. Finally, there's one crucial plotting guideline that makes this framework truly powerful: clustering. Inputs and functions that naturally occur together in a single instance of the scenario should be grouped as one cluster. Each cluster represents one coherent version of how the system operates. If another instance introduces different inputs or additional functions, that becomes a separate cluster. By comparing clusters, patterns emerge: what stays constant, what changes, and what truly differentiates one scenario from another. Those differences often reveal leverage points, constraints, or innovation opportunities. Taken together, this plotting technique turns complexity into structure. It helps you decompose scenarios, position their elements clearly, and reveal relationships in a way that is both rigorous and intuitive. All right, now that the framework is in place, let's bring it to life using a familiar and intuitive scenario: archery. Imagine an archer preparing to hit a target. The first thing we naturally look at is the equipment. A well-constructed bow, one that has optimal weight, balanced distribution, good string elasticity, and overall operational flexibility, makes it easier for the archer to perform well. As the quality of the bow improves, the effectiveness of the outcome improves as well. So, in our framework, the bow clearly belongs in the positive covariance of inputs zone. The same logic applies to the arrow. If the arrow is well designed and suited to the environment, its weight, straightness, and aerodynamic behavior all directly contribute to better results: better arrow, better outcome. So the arrow also sits comfortably in the positive covariance of input zone. Next, consider something less physical but equally important: target identification capability. The archer must be able to identify the target through sight, sound, or both, and the target must be reachable within the given conditions. The clearer the identification, the higher the chance of success. These two are inputs that positively influence the scenario, so they are placed in the positive covariance of input zone as well. Now let's shift to the outcome. What defines success in archery? Accuracy. The more accurately the target is hit, the more effective the scenario becomes. So accuracy is plotted in the positive covariance of functions zone because it represents the outcome whose increase directly improves effectiveness. At this point, we realize we've missed a critical input: the skill of the archer. Skill isn't static. It improves with time, effort, and focus. As skill increases over time, effectiveness increases too. This makes archery skill a perfect fit for the positive covariance of time-dependent inputs zone. Together, these inputs and outcomes, bow, arrow, target identification, skill, and accuracy, form a complete, stable snapshot of the scenario. We group them into a cluster, representing one coherent instance of how the system operates. Now let's pause and ask, what did we assume would not change? Certain things stayed constant throughout this analysis: the target itself, the accuracy measurement method, and the infrastructure between the archer and the target, including distance and basic reachability. Since these are assumed constant, we explicitly place them in the invariant and neutral factors area. Now comes the interesting part. What triggers a new cluster? Suppose a breeze starts fluctuating. Everything else remains the same, but this one new factor negatively affects the outcome. The breeze introduces a time-varying input that reduces effectiveness, so we plot it in the negative covariance of time-dependent inputs zone. Because of this breeze, accuracy is no longer stable. It now fluctuates over time. So accuracy moves from the static outcome zone to the positive covariance of time-dependent function zone. But we don't stop there. To stabilize the scenario under these tougher conditions, we introduce another input: practice in similar conditions. With more practice over time in similar conditions, the archer learns to compensate for the breeze, gradually restoring and improving accuracy. Practice, therefore, belongs in the positive covariance of time-dependent input zone. This creates a second cluster, a new instance of the same scenario under different conditions, showing how additional inputs rebalance the system and restore effectiveness. And that's the real power of this framework. It lets us decompose a scenario, see how inputs and outcomes relate, understand what changes over time, and clearly visualize how balance is lost and regained. To close this section, anchor on what you now have in your hands: a practical way to see complexity without being overwhelmed by it. By decomposing situations into structured parts and deliberately examining how those parts interact over time and across conditions, you move from vague intuition to explainable understanding. This is the point where analysis becomes usable, where you can justify why something works, what needs attention, and where intervention will matter most. With this approach, scenarios stop feeling tangled and start revealing patterns, trade-offs, and leverage. That shift, from seeing everything at once to seeing the right things clearly, is the real outcome of this stage. And it sets you up to apply the same clarity to any real-world problem you choose to engage with next.